Hi everyone, I'm back with another practice problem in signals and communications. Again, I'll write in the description who this video is useful for. Now let's dive into the question. Okay, it says a PCM system with uniform quantization is used to transmit a speech signal. The bandwidth of the signal is equal to 8 kilohertz. Okay, so in the PCM system, we can assume that the input is actually a sinusoidal wave. And then when it says the bandwidth is 8 kilohertz, that means that F0 or the fundamental frequency is 8 kilohertz. So F0 is 8 kilohertz. So this is by just reading the two first sentences, basically. Assume that the signal has a dynamic range that varies between minus 2 volt to 2 volt. So then we have A to be 2 as well. So this is another input we have. And then the range of the signal, which is we call L, is going to be 2 minus 2, which is going to be 4 volt. Okay, and then peak to peak value already said it's 4 volt. It didn't have to say that, but it's nice of them. And then that the quantization noise absolute value must be less than 2 millivolt. So AN of the noise is 2 millivolt. Okay, now what is the minimum sampling rate for the speech signal? Okay, so this one, easy peasy, Nyquist theorem, basically, or Nyquist-Shannon theorem, that says Fs must be equal or more than twice of the frequency of the signal, so that we have 2 multiplied by 8 kilohertz, that would be 16 kilohertz. So minimum Fs is basically 16 kilohertz. Then it says, what is the quantization step size? Okay, now this one first. So in case B, quantization step size, delta, we call it delta. We have to see how many bits we have to quantize this with, which is L over 2 to the power of n, and being the number of bits of sampling, basically. Okay, so this one, it seems like, oh, what is the quantization step size, but it requires some calculation. So we know that P noise is, if you consider the noise to be a sinusoidal wave as well, it will be, so the assumption is noise is a sinusoidal wave or signal as well. So this is the assumption, write it, okay? Then it's going to be AN to the power of 2, AN being the peak value of the noise. So we have 2 millivolt to the power of 2 over 2. Then on the other hand, we have, if the step size of the signal is delta, we have delta over 2 over 12, delta squared over 12, and then that is going to be 1 over 12, L, which is 4 volt, basically 4 volt, over 2 to the power of n, and then oh, actually, we don't need to go through all of that. We can just say, we found P.Eng here, and then we can relate it to delta here. And then we can say, so delta squared over 12 is going to be 2, there's 2, and then delta squared is going to be 12, 2, 10 to the minus 6. Delta is going to be a square root of 24, and then 10 to the minus 3 volt. So the quantization step is going to be We can calculate that. Square root of 224. Did I make a mistake? No. So about 4.9 millivolt. Okay, then it says in the signal quantization, what is the smallest possible number of quantization levels? Number of the quantization levels. So see, we have let's say number of quantization is going to be L over delta, which is 4 volt over 4.9 millivolt is going to be 816.3. So we can say smallest possible number is going to be 817 quantizations or steps. Then it says, now model the signal as a sinusoidal, model as a triangular wave, determine the SNR for the reconstructed signal. Okay. Now, so D, it says, if we assume this is our noise, so this is our AN basically, then and then our signal is basically, so we can say SNR is basically AN or PN, sorry, PN over PS, which PN we already found is going to be, because this is a triangular wave, again, the average or PN is going to be minus T over 2 of AN T dt, something like that. Basically, the triangular wave, the signal is going to be definitely AN over the squared over 2. So we the PN model that we already considered is okay. So we can say 2 10 to the minus 3 to the power of 2 over 2 volt multiplied by, or squared over 2. So here is going to be, I made a mistake, guys. SNR is PS, because I'm solving these for the first time with you. So PS is going to be 1 over 2 of the peak value, 2, and then this is going to be 1 over 2 of AN value. That's why this is going to be 2 volt squared. This is 2 millivolt squared. So it's going to be 10 to the power of 6. In SNR in dB is going to be 10 log of SNR value is going to be 10 log of 10 to the power of 6. It's going to be 60 dB. Pretty impressive. Okay, what is the bit rate of the PCM signal using the number of the quantization level in C and the sampling rate in A? Okay, so now the bit rate is equal to the sampling rate multiplied by number of bits that we would need. This is 16 kilohertz multiplied by number of bits. Okay, do you remember how many steps we saw, how many steps we calculated? So L over delta, if we assume that this has to be 817, has to be modeled by 2 to the power of n, number of bits, then n is going to be log of 817, 2. So that's about 124 is 2 to the power of 9. 512 is about 2 to the power of 9. Sorry, 10 to 24 is 2 to the power of 10. So this is between 9 and 10. So basically, n has to be about 10 bits. Almost, because 9 would be too little, and then 10 would be too much, but the minimum is 10 bits. So the bit rate is going to be 16 kilohertz multiplied by 10 bits is going to be 160 kilobits over second. That's how we calculate. PCM ones are quite easy, especially if you know the average powers for different signal models. I hope you learned something, and hit subscribe and come back for another practice problem. Thank you.